Let's start. So, remember last time, the last thing we covered was the Chinese remainder theorem. Looking through the proofs for that section, they're almost identical to just solving problems. You just do it with variables, and it gets kind of technical keeping track of when you're modding by n. So I don't think that there's anything to be gained from doing those proofs in class. So as long as you know how to carry out that operation, I think you're fine. Does that make sense, what I'm saying?
Yeah.
So solving a system of linear equations using the Chinese remainder theorem is almost identical to the proof. And you could, like if you were to look at the proof in the book and have a solution to the side at the same time, you can see exactly what they're doing. You'd be looking at the variables exactly as they use them. So it almost follows exactly like solving the problem. Does that make sense? So not going to bother with going over those proofs, proving that the Chinese remainder theorem works. You can go through that one on your own. So we're just going to continue to the next section. This is the last section in the chapter. After this, we have a test next week. And then I want to get your guys' input now so I can start knowing what to prepare for, which is what to do next. What I have in the syllabus to do next is algebra. The common terminology for what it is called abstract algebra. What that is building up basic structures and foundations that ultimately lead to an algebra. An algebra is a type of structure with properties. You know how every time we come across some new set of operations, we start saying it has the associative property, commutative property. Those are properties that that set had with those operations. So an algebra is a certain structure with properties and operations that go with it that satisfy certain properties. That's what algebra is. So when we're doing the abstract algebra section, it's just called algebra, but I'll say abstract algebra to help not confuse you from what you did in grade school. That is starting out with really simple structures that you use that ultimately lead to an algebra. So in that, we would never actually do an algebra. We would start with really simple structures called groups, and we'd work our way up. So that's what algebra is. The other way that we could go would be into graph theory. I closed my book. Let me see table of contents. Where are you? Oh, back. Okay, so the other way that we could go are graphs, and we could get into graph theory. From a high-level point, what a graph is, it's not what you think about like plotting a graph. A graph is a collection of nodes and edges. Here's a graph. Here's the most basic intuition for what a graph is. And so in graph theory, you start to study different graphs. You do proofs with graphs. You study different types of graphs, properties of graphs. For example, this graph right here is not a connected graph because there's no path I could follow from this node to get to this node. This, however, is a connected graph. Started at any node, I can get to another node. That's an example of a property a graph might have. So graph theory is the other way we can go. We can't go to partially ordered sets. Because we need graph theory for that one. So our choices are between algebra and graph theory.
Algebra. We don't have time for both of them.
Not likely. And I think if we go the algebra route, I left out the more computer science stuff. So I think we ended at 43 if we do algebra. I don't think I go to encryption. I can't remember where I put on the syllabus. But we could always bail out of algebra as soon as we wanted and then move on to graph theory if we want. So we could start with algebra, and then if a particular, once we get far enough in, if you guys feel like you're not interested in that material anymore, then we can stop at that point and switch over to graph theory. Does that make sense what I'm saying?
Yeah.
So you want to do graph theory?
I'm content to do any of it. I love it all. I'm just saying, so the algebra stuff is very universal, but once you get to the encryption stuff, because discrete math is a field that both mathematicians and computer scientists are typically required to take, and so the author sets up the textbook so that it works for both. So like, I think I accidentally gave you guys once a programming assignment on your homework by accident, because it's a common thing for computer scientists to do. So the encryption part, I mean, it's still interesting math, and I'll do that if you guys want to do that, if you want to learn how encryption works. It's just very computer science oriented, and you can learn how encryption works in general if you want, and we can look at how computers do that. So I'm happy to do encryption. I was just thinking you guys might not be as interested in encryption part about it. So I'm happy to do whatever you guys want. But sounds like we'll start out with algebra.
Okay.
Is that what you guys want? Because last year the group wanted to do graph theory.
Graph theory is pretty cool. I just doing like the little bit of research I have about what it is and what it's used for. I mean, it looks like it'd be really interesting.
It's another topic that's a lot more computer science oriented than I think algebra is more universal, whereas this is very computer science oriented because these are the types of data, this is the type of structure that we use over and over again to store data in. Different types of graphs, specifically things called trees, but you don't care about that. So,
I think algebra is a great we started. I mean, we might have a little bit of extra time at the end anyway.
we might. I was looking at doing constructing the natural numbers, and I think that's a bad idea.
Why?
Because then we gotta start with logic. It's like, if you're gonna do that, start right. And we have to do a logic course.
How long does that take?
It's what I'm most likely going to do over the summer,
Oh, that'd be cool.
is a logic course. And in that logic course, we would do exactly that. We construct the natural numbers, we go over the basics of set theory, and we'd start with just logic. So I think that that's the right way to do it. If you're gonna go far that back, may as well go all the way back. What I thought we could do, if you guys were more interested in it, was start with the natural numbers and construct the reals from the naturals. So you start with multiply and addition on the naturals, and then from there we would construct the integers, the rationals, and the reals with the different properties that they have. That's something that we could do. That's a more natural beginning spot than trying to construct the natural numbers just out of the blue, because then it really seems like we need to start with logic. So,
Could we just use our last class for that?
sure, we could do that whenever you guys want. I'm saying that's something that we could schedule in if we have more filler time, as opposed to another section in the book if you want.
Okay.
So keep that in mind. So next week we'll have the test, and then the week after that I'll come prepared to start algebra.
Would we be starting next week? After that?
Oh, yeah, after the test. Sorry. I'm mixing you guys up with my calculus class. My calculus class, I have a full 3-hour test.
So whatever we study next, are you going to put into the midterm or final?
Yeah, most likely. I don't know. Maybe I'll be lazy and use the final that I used last year, which ended with, this was the last section that we formally covered. And then we just quickly went through graph theory without doing any tests or homework because we only had like 2 more weeks until school was out. So.
How are we so ahead?
We're more on schedule. They're more behind. They were more behind.
Right.
You guys are a smaller class than they were. I think I had 8 or 9 students in that class. And then you guys are all pretty much on the same level of class. I've never had a class this uniform where you all kind of get it the same. Usually I've got a class where there's like one student who they've already checked out, one student who's really trying not to check out, and they're just chugging along, struggling as much as they can. a couple students who are where you guys are at, and then a student who's just like, after 10 minutes into the lecture, they're already kind of bored, they know where it's going. So you guys are a class that's all like right here, instead of having the checkouts, the real strugglers, and then everyone's kind of getting it, and then the people who are just, it's really easy for them. So, you guys are like the perfect class to teach. Don't have to worry about all the different levels. So that's why, it's because those people who are struggling to get behind, I mean, when you see a kid really trying, you don't want to give up on them. You don't just want to power through the material and let them get lost. The cost of that is the material's lower than you could have otherwise with a class just like you. And then another part of that is I just know what I'm doing a lot more this year. I mean, last year was my first year teaching it. And what did I do to prepare for teaching it? I took the class. It's like you guys going and teaching this next year. So, you'd be a lot more prepared if you had a year teaching it. Teach it again. Did I hit record? I have no memory of that. Okay.
I'm pretty sure you're.
Well, it's not there. You know who to blame. Okay, so yeah, next week I'll be ready for the first section on algebra. And I think that's why I already put into the syllabus, so I think we can just follow the syllabus.
How long will algebra take?
I don't know.
How long is it?
I don't know.
Is it 2 chapters?
It's
or
oh
what?
no, it's just one chapter like everything.
Okay, so it's 1 chapter, 2 takes.
Do you have the syllabus? Put it in the syllabus.
Yeah, I'm just too lazy to do that.
So you want me to guess at what's in your book versus you pointing at the syllabus?
6 sections.
There's 6 sections, but I didn't put all of them in the syllabus.
So it'll take what, 3 weeks? 2 weeks?
So we're still gonna
3
be
weeks?
like a month and a half.
We'll see.
Can we just like not do?
Because if it's 3 weeks of algebra, then we do the test at it. We can't cover more material after your last test. And then your final has 5 weeks of material.
An entire week of review, probably.
So,
Second
don't have as much time as you think.
We'll have maybe 2 or 3 weeks left again,
What's
maybe
a
3
couple
weeks.
months after that?
We will? We'll see.
We'll be halfway through April.
Because I think how I counted it is if we stick with the syllabus, right now I think we only have 1 more cushion week.
Yeah.
So I think I right now only have 1 week of material not planned out in your syllabus. And when I start the year, I give myself 3 weeks. So we lost 2. Anyways, so let's go over what we're going over today. And this is like your first real intro to number theory. If you ever take a number theory course, this is like chapter 1, chapter 2 material. This book kind of ends with number theory, like right where it gets going. So this is when we first get to start doing some real stuff with like prime numbers, which is one of the foundation concepts of number theory. In fact, we'll go over the fundamental theorem of algebra, which is of arithmetic, thank you, not algebra. Fundamental theorem of arithmetic, which is that every positive integer has a unique prime factorization, which is up to order. So this is the main theorem that we're going to be working up to today. Let's give you some intuition for what that means. What that means is pick any number you want, 24. I can express this as a unique prime factorization. So what are all the primes that go into this? We have 3 2's, and we have 3. Those are the prime numbers that multiply together that give you this. And these are the only prime numbers that multiply together give you this. The reason we say it's unique up to order is you could have also written this 3 times 2 to the 3. So you could have changed the ordering that you're multiplying in, but the prime numbers themselves that you're multiplying together are going to be unique. So every positive integer you can think of has a unique prime factorization. Now there's one case that you should be thinking, like, wait, what about
1?
1? What's the prime factorization of 1?
Doesn't have 1.
It does.
Because it's not a prime number.
No, it's not a prime number. But it has a unique prime factorization. What are
Anything to the 0?
Numbers that multiply to be 1.
And this one's kind of a trick one. And to understand why it is what it is, you need to go back to what is 0 factorial equal to?
1.
1. What's another way that we can write 0 factorial? Let's take the product of all the numbers starting at 1 up to 0 of k. And what do we get? We get 1.
I still don't get that. Why is that again?
Why is that again?
Yeah.
Up to 0, starting
I
on.
forgot.
Yeah, exactly. So when you're taking the product of no numbers together, the result is 1.
Why?
So,
Yeah, why isn't it 0?
Remember we talked about it.
yeah, we've had a discussion. Let's just reference a section. You can go back and look at that.
Okay.
It's because in common scenarios when you want to multiply things together, if someone had nothing to multiply and you took the product of what everyone was multiplying together, if you did 0, the whole product comes out to 0. So for example, let's say I'm trying to multiply all the numbers between 1 and 10. Okay? I say you multiply all the numbers between 1 and 5, you multiply all the numbers between 5 and 5, you multiply all the numbers between 5 and 10. And then I'll multiply together everything you get.
Okay.
Your product will be whatever it will be. If we make his product 0, the whole product just went to 0.
Yeah.
So if he's multiplying together no numbers, that's 1.
Oh.
That was the intuitive reason that he gave for it, and you can reread what the author has to say about this. So the empty factorization is the one that gives us 1.
How do you, is there another way to write 0 factorial, or is it just 0 factorial?
0 factorial is how we write it. I mean, what I had written there was our definition for 0 factorial. That product. So, anyways, 1 has unique prime factorization. That's the empty factorization. 2 has unique prime factorization. 2. 3 has unique prime factorization. 3. 4 has unique prime factorization. 2 squared, etc. So every positive integer has a unique prime factorization up to order. You can change the order that you multiply terms together in, but the prime numbers themselves, that is unique. Fundamental theorem of arithmetic. So that's ultimately what we're going to be working our way to proving. We need a couple lemmas first, and then we'll do this proof. This is the heart of the section. And then we'll do a couple more proofs that follow after this.
Okay.
Good?
Mm-hmm.
Alright, so let's start out with some of our lemmas. Okay, so if I've got 3 integers a, b, and p, where p is a prime number, and if p divides the product of a and b, then p divides a or p divides b. Good?
Mm-hmm.
Alright, that's what we're going to prove. Okay, so let's set it up. Let a, b, and p be integers where p divides a times b and p is prime. Just setting up what the problem gives us. We're going to assume by way of contradiction that p does not divide a and p does not divide b. So remember, we're setting up an impossible scenario, and we're going to show that that leads to an impossible worldview. P divides 1. We're going to show that if p doesn't divide either of those, then p divides 1, which is impossible.
So is this the proof that shows it's absurd? What's it called?
Reductio ad absurdum.
Yeah.
Yes, proof by contradiction, reductio ad absurdum. Here's an absurd statement, therefore our assumption was false. Good?
Right.
So that's ultimately where we're going. Okay, so we know p doesn't divide a, we know p doesn't divide b. Then a and p are relatively prime. How do we know that? I know that the only factors of p are what?
1 in itself.
1 in itself. And if p is not a factor of a, then the only common factor that these two have is 1. You know what it means for them to be relatively prime? It means that their greatest common divisor is 1. That makes sense? So if a number isn't a multiple of a prime, then those two numbers are always relatively prime. Their greatest common divisor is 1. So look at 7 and any number. If I have 7 and you pick any number here that's not a multiple of 7, like 10, then their greatest common divisor is always going to be 1. Because their divisors have to be 1 or 7, because that's all that divides this. Okay, so if if whatever A is, if P doesn't divide A, then A and P have to be relatively prime. Same thing. And B and P have to be relatively prime since P doesn't divide B. So you good with up to here?
Yeah.
Okay. Here's that theorem that I told you was the theorem that we were going to use the second most in this chapter. It's the theorem that if two numbers are relatively prime, then some sum of multiples of those numbers produces 1. So if A and P are relatively prime, then there exists an x and a y that are integers such that this sum equals 1. And in finding these numbers x and y, that's something we did over and over again. You had to use Euclid's algorithm to do that. That's when you're doing the back substitution. That's when you're finding that x and that y. Remember that? Similarly, since B and P are relatively prime, there exists z and w such that the sum of this product is 1. You with me on all that? Okay, so here's how we're working our way towards this contradiction. So 1 is equal to 1 times 1. Make sure that makes sense. Which is equal to 1 times 1, using the fact that that is equal to 1 and that is equal to 1. Good? Distribute all that out. The important thing to know is that this term has a p in it, this term has a p in it, this term has a p in it. We're going to show that this term secretly also has a p in it. Therefore, 1 equals p times something, and so p divides 1. That's where we're going. So right now the problem is we don't see a p here. We see a p here, we see a p here, we see a p here. So we know that p, so if this secretly has a p in it, which it does, then we can factor a p out of all this. So 1 equals p times this whole sum, so p divides 1. And a prime dividing 1 is impossible.
Right.
Okay, that's where we're going. So here's how we have it so far. We have this term that doesn't have a p, plus we factored a p out of these three terms. Okay. We're going to come back to this equation. Side note. Since p divides a times b, remember that was our given. P divides a times b. It just doesn't divide a and it doesn't divide b. Sorry, I wrote that. I said that in the wrong spot. P is a prime. P divides a times b, but p doesn't divide a and p doesn't divide b. But it does divide the product. So, since p divides a times b, then there has to be some integer k such that pk equals ab. Right? So that's the substitution that we're going to make into this equation right here. We're going to replace this ab with a pk and then factor out the p. So instead of abxz, it's now pkxz. And then we still have the p factored out of these terms. You see how I'm getting from here to here using that substitution?
Yes.
We're just replacing the AB with the PK and then factoring out the P. Okay. So 1 equals P times something. Therefore, P divides 1. Contradiction. Can't be true. Therefore, P has to divide A or P has to divide B.
I feel like there should have been an easier way to do that.
Maybe.
Couldn't you have said PK equals AB and then divide by K? No, that doesn't work. Never mind. Maybe, we'll see.
Yeah, we got to be careful about dividing by K in the integers.
Yeah.
Okay, so that's that lemma. Now let's do this one. This is going to be approved by induction, so I don't want to lose you in the details, so let's make sure what the lemma is saying makes sense first. So if I have P is a prime, and then a bunch of other primes, Q1, Q2, Q3, Qn. So I have P is a prime, and then all these other primes. If P divides the product of all these primes, then at least one of these primes has to actually equal P. You follow me on that?
I'm starting from the first prime.
Well, it's just arbitrary primes. So if I have some arbitrary set of primes, 3 times 5 times 7 times 2 times 13 times 11, and maybe we got that squared, maybe we had 4 of those. If I have a prime here, that divides this product, then it has to be one of these numbers.
Okay.
That makes sense? So, for example, I know that 17 does not divide this. None of those numbers are 17. However, 13 does divide this because one of those numbers are 13. So, the part I don't want to lose yet is the subscripts. We're saying if P divides this product of primes, then P is equal to one of those primes. P is equal to some Q sub I, where I is between 1 and n. We're just saying one of those primes had to be P. And we're going to prove this by induction. So we're going to start out with showing that if P divides one prime, then P is equal to that prime. With me so far? Okay. Then we're going to assume P divides K primes. So what do we mean by that? We mean anytime you take K primes and multiply them together, if P divides one of them, P is one of those primes. And we're going to show that implies P dividing K plus 1 primes always. Or if P divides K plus 1, then P is one of those K plus 1. Let's just go through it. Maybe I'm trying to over-prepare you for it versus just going through it. Okay, so proof by induction. How does proof by induction work in general? If you want to show that a set is equal to the natural numbers, you show that if 1 is in A and K in A implies K plus 1 is in A, then A is equal to the natural numbers. That's high level the way it works. So we're going to show if A is the set of all the numbers it's true for, we're going to show it's true up to 1 for 1, and we're going to show if it's true for K, then it's true for K plus 1. Therefore, it's true for all natural numbers.
Can't you start with 0 too?
Well, it doesn't make sense to have 0, P divides 0 primes.
Not in this case, but like you could, right?
Yeah. Oh, sorry. Yes, exactly what you're saying. I forget, naturals in this class include 0,
Yeah.
whereas in calculus they don't, so I get a little confused there. But yeah.
Is there a notation where you can write like a really large set, subtract one number or one element?
Sure.
Or just a couple, maybe?
Sure. So here is Z. In fact, I think in this class it's just this.
Yeah, okay, I remember.
But in a lot of books they do that for the set subtraction. So that's all the integers except for 1 and 2. Okay, anyways. So first we're going to prove it's true for the case where n is 1. Assume it's true for the case where n is k, and show that means it's true for the case where n is k plus 1. Therefore, it's true for every positive integer. Good? Alright, so base case, for n equal to 1, if p divides one integer, or if p divides one prime number, then those two numbers are equal since they're both prime. Right? If a prime number divides a prime number, they have to be equal. Does that need more explanation? Or are you good with that?
That's good.
Okay, so p is equal to q1, q sub 1, where 1 is in between 1 and 1. Notice we're saying every time p divides n prime numbers, then p is equal to q sub I for I between 1 and where we ended. So p is equal to q sub I for I between 1 where we ended. Being a little bit explicit here so that you can see how the next part works, but you understand how this is satisfying the statement?
Well, that last number, n, doesn't really matter if you put that, right? As long as it's greater than 1. Or equal to. So it could be 1, but in any case, it would work.
We're showing that for any positive integer you put here, this is true.
Right.
Right. So we showed if you put 1 here, it's true. Now we're going to assume it's true if you put k here, and show that implies it's true for when you put k plus 1 here.
Right.
Good? Proof by induction. Okay, so assume for n equal to k, whenever you have p divide the product of k prime numbers, then p is equal to one of those prime numbers. It's equal to q sub I for some I between 1 and k. Assume that's the case. Remember, we're doing this part. How do you prove that this implies this? You assume this is true, and show that leads to this being true.
If we use 1, 1 isn't a prime number, so are we using it just for the proof proof by induction, or?
1 was for this number.
Oh, okay.
We don't know what the prime numbers are.
Well, didn't you choose one?
It's for any prime numbers.
Okay, right.
For any prime numbers that satisfy this condition, this was also true. Make sense? Okay, now we're assuming you can take any k prime numbers you want and multiply them together. And if p divides that k product, then p is one of those k prime numbers. That's what we're assuming. And we're going to show out these being true when you put k plus 1 there. And you multiply k plus 1 prime numbers. With me? Okay. Then it remains to show that if p divides k plus 1 prime numbers, then p is equal to q sub I for some I, that's supposed to be an I right there, for some I between 1 and k plus 1. That's what we need to show. And then we're done. Make sense? Okay. So since p divides this product, since p divides q1, q2, all the way up to q sub k plus 1, then using this proof over here, p divides either this whole thing or this thing. We can arbitrarily split this into two factors, right? I can multiply all these together and call that one number. I can put parentheses here and call this one number. And then multiply it by that, right? No rule against sticking parentheses in there. So since p divides whatever this number is times this number, then by our previous theorem, p divides either this number or p divides the last number.
Right.
You follow that? Using our last theorem right here. Well, if p divides these numbers, then by assumption, p is equal to one of those numbers for I between 1 and k. That's exactly what we assumed up here. We said anytime you're multiplying together k prime numbers, if p divides it, then p is equal to one of those k prime numbers. So, if p divides k prime numbers, then by assumption, p is equal to q sub I for one of those prime numbers. For I between 1 and k.
Okay. Yeah.
You with me on that?
And yeah, and we proved that that's possible in step before too, right?
No, we proved it was true for 1. We assumed it was true for k. And show that leads to being true for k plus 1.
Right. So what I'm saying is we know it's possible in at least one case.
Right, we know it's possible in the case for 1.
Right.
So we did that, right, so if p divides the product of k prime numbers, then p is one of those k prime numbers. Then, otherwise, if p divides the last term, right, we're handling two cases. Either p divides this or p divides this. Those are the two cases. So, if p divides the last term, then p is equal to the last term. Right? If a prime divides a prime, then those primes are equal.
Oh, okay.
Yeah.
Yeah? Okay. Sorry, I didn't know we were getting that. So, then those primes are equal, which means p is equal to q sub I for some I between 1 and k plus 1. Namely, in that case, it was k plus 1. So, if I divides the first term, then there was an I between 1 and k, such that p equals q sub I. And if I divides the last term, then there was, or if p divides the last term, then there was an I between 1 and k plus 1, such that p was that ith term. Right? So in either case, p equal to q sub I for some I between 1 and k plus 1. If it divided the first k terms, then there was a term that it equaled. If it divided the last term, then there was a term that it equaled. So in either case, there was always some q sub I term between 1 and k plus 1 that it equaled. That's our proof by induction. Therefore, if p divides n terms, then p is equal to one of those. If p divides n primes, then p is equal to one of those primes. You follow the proof? Okay. So now we're ready for the fundamental theorem of arithmetic proof. book because I went to the table of contents. Let's see, factoring is 279. Okay, so now we're going to do this proof, which I think you guys already have an intuition for what this is saying. So we're going to kind of break this up into two parts. First, we're going to show that every positive integer has a prime factoring, and then we're going to show that that prime factoring is unique. You see what I'm saying? Okay. So let's tackle it. We're going to do this by smallest counter example for showing that a prime factorization exists. So let big X be the set of all positive integers that don't have a prime factorization. You can't factor them into some number of prime numbers. Good? Assume, by way of contradiction, that X is not empty. We know that there are no positive numbers that can't be factored into primes. We're going to assume by way of contradiction that there is at least one positive integer that can't be factored into primes. So an impossible statement, right? And then we already talked about why 1's not in X. 1 can be factored into prime factorization, namely the empty factorization. Since 1 is the empty factorization. Little reminder of y right there. And 2 is not an X since 2 is prime. 2 has a prime factorization, namely itself. So whatever elements are in X, whatever elements don't have a prime factorization, they at the very least aren't 1, and they at the very least aren't 2. So they have to be greater than 1 or 2. Because we're talking about positive integers here. You with me? So far the smallest possible thing in here is 3. You good? Okay. So by the well-ordering principle, there exists a least element of big X. We'll call it little x. So we know that little x is greater than 1, right? Because 1's not in there, so x has to be greater than 1. And we know that x is not prime. How do I know that little x isn't prime?
Because then it would factor into primes.
Because it factors itself, right? It itself is its own prime factorization. So it can't be prime, and it's greater than 1. So it's a non-prime number greater than 1. We have a name for those numbers.
Composite.
It's a composite number. Right? It's not prime, it's greater than 1, therefore it's composite. And what does it mean to be composite? If it's composite, then there exists some integer a between 1 and x, such that a divides x. Right? That's the definition of it being composite. Well, if a divides x, what does that mean? Then there's some integer b, such that a times b equals x. Little x here. Now we know that because a is positive, then this integer b also has to be positive. X is positive and a is positive. We can't multiply a by a negative integer to get x. So therefore b is also positive. Let's see how I want to say this. The next thing I want to say is that b is also greater than 1.
Not necessarily, right? Oh, yeah.
Yes, necessarily.
Because a is less than x.
So let's see how we can make that make sense. So I know that 1 is less than a, right? Is equal to x divided by b is no, that's not how I want to say it.
You could just say that because A is less than X, B has to make it bigger.
Well, yeah, I know that b has to make it bigger because if b were
1, then it would
1, then that would make a equal to x,
Right.
which we know isn't possible. I wanted to just show some nice algebra to make it make sense. Let's see the author's algebra. Let's see how they say it. Because 1 is less than a, we can multiply both sides of this. Oh, that's a way better way to say it. Okay. Since 1 is less than a, multiply both sides by b, we get b is less than ab is less than x, or is equal to x. No, that still didn't give me where I thought. Maybe I was in a different part of the proof. To multiply both sides, we get b is less than ab. Thus, where do you say b is greater than 1?
You could have, no.
Oh, here we go. Since a is less than x, that gives us divide both sides by a, and that gives us 1 is less than b. There we go. Divide both sides by a. A divided by a is
1.
1. X divided by a is
B.
b. So since x is greater than a, then 1 is less than b. And then we also need that b is less than x. And that's what the next part was that I should write.
Well, since it's a factor of X, it can't be greater than X.
And then since 1 is less than a, that gives us multiply both sides by b. B is less than x.
Oh, okay.
You could say about factoring, that just appeals to our intuition real strongly, but a hard argument to put on paper, because like it gets real wordy.
Yeah, it gets wordy.
Okay, so the point is, a and b are factors. X can be written as a and b, where a and b are both less than x and greater than 1. So a and b are positive integers less than x. You with me? So what does that mean? Remember, x is the smallest thing that what?
That doesn't have a prime factorization.
That doesn't have a prime factorization. So a and b both have a
Prime factorization.
prime factorization. You with me on that? Then both a and b have a prime factorization, which gives a can be written as P1 times P2 times ... times Pn, and B can be written as Q1 times Q2 times ... times Qk. Right? If A A and B have some prime factorization, and there's some number of primes I can multiply together to get A, and some number of primes I can multiply to get together to get B. You with me on that? Then, what does that give us? Where's our big contradiction?
Well, the factors are prime. Factors of A and B are prime, and A and B are factors of B. So
Of what?
P, X. Sorry.
X. So then X is equal to
All those prime numbers.
P1 times P2 times dot 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 times Pn times Q1 times Q2 times dot 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 times Qk. Contradiction. Right? We just barely found our factorization, a prime factorization of x. Remember, x was the smallest positive integer that didn't have a prime factorization. It was the smallest one. We found two integers a and b that were smaller than x, so they had to have a prime factorization, and it just turned out that their product was x. So multiplying together, you get x. So multiply the prime factorizations together, you get x. You see the contradiction? Okay, so we proved the existence part. Now we need to prove the unique part. So, where are we? So now, assume by way of contradiction that there exists we're going to have to use the least element. So let's start by setting up our set. We'll use y since we used x here. So let y be the set of all positive integers with more than one prime factorization. Okay, and we're going to do exactly what we did by 4. 11, assume by way of contradiction that y is not empty. Assume by way of contradiction that y is not equal to the empty set. Observe that what's not in y, 1 is not in y. It has a unique factorization.
So are you proving by smallest counterexample again? Or?
Yeah, smallest counterexample again. So observe that 1 is, assume by way of contradiction that y is not equal to the empty set, comma, and let little y be its least element. We need to get the least element out of that thing. Be its least element. 12. Observe 1 is not in y, which gives us that little y has to be greater than 1.
Wait, what? How do we know 1 isn't in y?
There's only one way to write the empty set. Any other primes you put in there, you're going to get a number bigger than 1.
Wait, what?
The unique prime, the only prime factorization of 1, here are its prime factors. The empty set. there's only one way to get the empty set. There's only one way to count that. It is?
How is y greater than 1?
Because 1's not in here.
Yeah, y
So-
is.
So big Y is the set of all numbers that have more than one prime factorization. Right?
Okay.
Little y is the smallest number in Y, in big Y. So little y is the smallest positive integer that has more than one prime factorization.
Alright.
1 only has one prime factorization. The empty factorization. There's only one way to do that.
Therefore y is.
Therefore, little y has to be greater than 1. So 13. Then there exists, I want to say 2 factorizations that equal y. Then there exists 2 unique factorizations of little y. I'm going to use p and q again, so don't get confused by what we have down there. Y equal to p1 times p2 times dot 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 times p sub n, and y equal to q1 times q2 times dot 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 times q sub k. This end of the list that have no elements in common. Okay, so first thing we're going to show is that it's impossible for any of these prime numbers to be the same as any of these prime numbers. Any of them. So not only are these two things unique, but these two things can't have any prime numbers in common. So how are we going to say that? Observe that if P1 times P2 times that times Pn had any factors in common, had, not any factors, we'll just say a factor, had a factor, and we'll call it, what should we call it? R. R in common with Q1 times Q2 times dot 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 times QK, comma, then Y over R would have 2 unique factorizations. So notice, so we're assuming that y has 2 factorizations, right? And it's the smallest number that has 2 unique factorizations. If any of these factors were in common, just divide them out, and the number that you get would be smaller than y, and it would have 2 unique factorizations. So if r was a factor of this, and r was a factor of this, then y divided by r gets rid of that factor from both those factorizations. So y divided by r would be a smaller number with 2 unique factorizations. You see what I mean?
Yeah.
So that can't be the case. So these 2 factorizations can't have any factors in common. Let's say that one more time. Y is the smallest positive integer that has two unique factorizations.
Okay.
If two of its factorizations had a common factor, namely r. So if P1 times P2 gave you r, and Q2 times Q3 gave you r, if they had any factors in common, then we could just divide both those numbers by r, and we still have the same number, right?
What do you mean? You have the same.
So this prime factorization equals this prime factorization.
Right.
If this has an r in it and this has an r in it, divide both those by r and you get a new number.
Yeah.
That's equal. Right?
What's equal?
If I divide both these numbers by r, I get another number that's equal. This number equals this number,
Why?
because they're both equal to y. Okay. Y is the smallest positive integer with two unique prime factorizations. So y is equal to 2 times 3 times 5, and it's also equal to 17 times 19. Something like that.
Okay.
It's the smallest number that has two unique prime factorizations.
Okay.
So all these primes multiplied together equal all these primes multiplied together.
Okay, yeah.
If these two products of primes have any number in common, any factor in common, namely r, then when we divide both these factors of prime by r, we get a smaller number. So take this divided by r, you get a number. Take this divided by r, you get a number. Furthermore, those two numbers you get are equal to each other.
Okay.
So if they have a factor in common, namely r, then y divided by r is a smaller number with two unique factorizations, which isn't possible. Y is the smallest number with two unique factorizations. If any of these factors are in common, if any of these have a common factor, namely r, then y minus r would have two unique factorizations and it's smaller than y.
Right.
Okay, so we know that if there is an integer y with two unique factorizations, they at the very least can't have any common terms. None of these prime numbers are the same as any of these prime numbers. That makes sense? Okay. 15. Now, since P1 divides y, right? Because P1 times P2 times all these equal y. Since P1 divides y, that gives P1 divides y. Right?
Yeah.
So we did 37 and 38 last week,
Probably.
and we're doing 39 today.
Yeah.
Probably. So since P1 divides y, P1 divides y, which gives us P1 is equal to Q sub I for some I between 1 and k. By this theorem. If a prime divides some product of prime numbers, that prime is equal to one of those prime numbers. So we know these two prime factorizations have no prime numbers in common. But they have to have a prime number in common. Contradiction. Therefore, every positive integer has a unique prime factorization. Is that a knock on our door? Come in.
So sorry, I took the start.
All good.
I'm wondering if I can borrow
basic arithmetic. And it helps us do really basic things, like finding the greatest common denominator, greatest common divisor between two numbers.
So why did we go over this first?
We needed this theorem. So you use greatest common divisor to get you to this theorem. This theorem helps you prove the fundamental theorem of arithmetic, and then the fundamental theorem of arithmetic helps you find greatest common divisors. You don't need it to find greatest common divisors, and it helps you find greatest common divisors. So how do we find the greatest common divisor? If I say find the greatest common divisor between this number, 7 cubed 19 squared times 2 to the 8, whatever that number is, but here's its prime factorization, and 7 squared times 17 cubed times 19 times 2 to the 3, what would its greatest common divisor be?
19.
You just take the common divisors between, you take the common prime factors between the two numbers, and that's its GCD. The GCD between this number and this number is 7 squared times 19 times 2 to the 3. Whatever that number is a common divisor of this, and it's a common divisor of this, right?
Mm-hmm.
Furthermore, it's the greatest common divisor. Because it's the most prime numbers you can get that go into this, and the most prime numbers you can get that go into this. So if you can factor a number into its prime factorization, it turns out real easy to find the GCD. Unfortunately, we don't have a great algorithm for factoring a number to its prime factorizations. But if we did, turns out finding the GCD between two numbers is really fast. And this is actually how, if you're interested in this, so RSA encryption, the encryption that computers use, rely on the fact that it's really hard to find the prime factors of a number. Make sense? So in some way they use the fact that it's really hard to find the prime factors of a number to break the encryption. Well, the reason that quantum computing breaks prime factorization, or breaks RSA encryption, is because there's actually a quantum algorithm that you can run on a quantum computer that finds prime factors really fast. And that's how it breaks it.
How does that work? Is there even a way you can explain it?
No, even explaining how a qubit works is a bit of work. And why classical computer, if we're going to call it that, we call it classical mechanics and quantum mechanics. So a classical computer and a quantum computer differ fundamentally. The quantum computer doesn't, the number of states it can hold is not, I can give you some basic intuition. So for example, if you only give me 4 bits, then the number of states I can hold in those 4 bits, there's only 16 different states I can hold. I can do all zeros, 0, 0, 1, 1, 0, 0, all the combinations of zeros and ones that I can do in those 4 bits are all the different states that I can hold in my quantum computer. Or in a classical computer.
Right.
In a quantum computer, I can hold, well, how can I say this right?
Is it
No, I'm going to
twice
say
that?
that wrong. No, it's an exponent. It's, instead of it being, so here we can hold 2 to the 4 different states. In a quantum computer, how do I get my thinking right?
Would it be 16 squared?
I want to say it would be this, but I'm trying to get my thinking straight for explaining it. 2 to the 16. I'm not going to explain it right. Not with the intuition. I know I could if I thought about it more, so I'll have to think about that and retry it. But I know there's a way I can make it make intuitive sense. Anyways, so there's the fundamental theorem of arithmetic. That's almost the end of the section. We have 2 more proofs to do. So maybe we'll go on break real quick since I've got to erase the boards anyways. And then when you come back, we have 2 more proofs and then we're done with the chapter.
Before you raise, can I take a picture?
Oh, yeah, sure, sorry. big cheeks,
She's
but
got tips and eyebrows.
she's actually under the average weight and way over the average height.
Really?
Yeah, so not only is she under the average weight,
How
but
old is
she's
she?
tall. Let's see, she's gotta be about 7 months now.
Oh. Yeah, she's pretty big.
So, but for some reason, she's just got big cheeks.
Mhm.
And then that bow on her head makes them look even bigger.
Okay, so I'm so confused. What is this stuff again? These big circle.
Modular addition and modular multiplication.
Right.
So, it depends on the Z you're in, but assume that you're in something. Z10. Okay. Then 3 plus 8 is equal to 3 plus 8 mod 10. Where remember, what is mod 10? It's the remainder after you divide by 10. So 3 plus 8 is 11. What's the remainder of 11 mod 10? Or what's the remainder of 11 when you divide by 10? 1. So this is equal to 1.
So 3 plus 8 is 1.
So 3 plus 8 in this sense is 1. Because this plus means do this. Take the sum and multiply 10.
Okay.
I also have a question about homework.
I will be here after school, by the way.
Okay.
You will or won't?
Will.
On a few of the problems we're saying you should check, but you should solve the problems by guessing and checking when you have to find their inverses and stuff
Right, for smaller sets.
for smaller sets. And I was thinking, how can you find the inverse if we prove that you find the inverse by using extended Euclids?
Extended Euclids always gives you the inverse. But sometimes the math of doing extended Euclids is more work than really quick checking all the numbers in the set.
Right, well, for example, one of my problems, when you think about, when you do math or whatever, you don't find an inverse, but by guessing and checking, you do find the inverse.
No, extended Euclids always gives you the inverse.
Okay. Maybe I need to relook at my problem, make sure I copy anything straight.
Have we made any progress on our activity that we're doing?
Pause when hurricane happened, but
What'd you say?
just asking about if we made any
No,
progress.
what did you say?
Said it kinda got paused when we did the hurricane.
Yeah. I think we're planning on doing test evening for the game sometime in the next week or two.
Oh, yeah, that's right.
Might be this Friday.
Alright, let's do the last two proofs real quick, and then you guys can have the rest of class. That way we don't carry out the recording. That's what we need. Okay, so the last two proofs we're going to do is we're going to prove that there's an infinite number of prime numbers, and then we're going to prove that square root 2 is irrational using our prime factorization over there. And then this proof of an infinitely number of prime numbers, this is a Euclid has a proof of this clear back in his Algebra, so.
With the geometric proof?
Kind of, yeah. They think about numbers different than we do, so it's the same basic idea, but his idea is representing numbers with line segments. But yeah. Okay, so there are infinitely number of primes. Assume by way of contradiction that there are n primes. There's an n number of primes, not an infinitely number of primes. Then we let k equal the product of all the prime numbers together plus 1. Notice that k can't be a prime number since k is greater than all the prime numbers, right? So k is a positive number, and it has to have a prime factorization, according to our theorem over there. If it has a prime factorization, then there has to be at least one prime that factors into k, right? It can be expressed as k prime factors, at least one prime factor p divides k. There's one factor of k. There has to be at least one prime factor of k, right? However, anytime you divide k by a prime number, then there's going to be a remainder of 1. K divided by this gives a remainder of 1, k divided by this gives a remainder of 1, k divided by this gives a remainder of 1. K divided by any prime number gives a remainder of 1. Therefore, no prime number is a factor of k, which contradicts our fundamental theorem of arithmetic. That every positive integer can be expressed as a prime factorization. Make sense?
Mm-hmm.
Pretty simple proof. I don't know if I lost you some of the notation there, but the idea is pretty straightforward. Multiply all the prime numbers together, add 1. Now you have a new number that isn't divisible by any existing prime number. The way that Euclid did it is, he said, assume that there's n prime numbers, here they are, then plus 1. Now you got a new number that's not divisible by any of these prime numbers, therefore it's prime, by definition of prime. So you just created a new prime number, making there n plus 1 prime numbers, but you assume that there were only n prime numbers. That's Euclid's thinking, but this thinking works too.
So it's kind of like a proof by induction, where he does it. There is a prime, and then because of that, there's an infinite number of primes.
Well, assume that there's a finite number of primes. Assume that there's only n. We just show, okay, now there's n plus 1.
Right.
Going against our assumption, so it's proof by contradiction, it's not a proof by induction.
Right. Right.
Okay, and then prove that square root 2 is irrational. I think we did this early in the class using the definition of odd and even.
I think we did this much earlier.
Maybe.
Yeah, but even if we didn't, here's a simple way we can do it with using this proof that we just came up with. So we're going to prove that square root of 2 is irrational. Assume by way of contradiction that the square root of 2 is rational. Or in other words,
Wouldn't that be in R instead of Q?
no, R is real numbers, Q is irrationals.
Oh.
Q is a set of all the quotients of integers.
Right.
If you can express a number as a quotient of integers, it's a rational number. So assume that there's some quotient of integers such that when you square it, you get 2. Right? That's what it means for the square root of 2 to be rational. If you square it, you get 2. So then there has to be two integers a and b that x is equal to, such that their square gives you 2. Right? Which is the same thing as a squared equals to b squared, where a and b are integers. You with me so far? Okay. So now think about it. Is this a positive integer? Yeah. Any integer squared is positive. Is this a positive integer? Yeah. So we have two positive integers. Therefore, they have to have a unique factorization. A unique prime factorization, right? They're equal to each other, so they have to have the same unique prime factorization. Right? But in a squared, however many 2's there are, it's going to be an even number. Because you're squaring it.
Right.
So there's always an even number of 2's that you multiply together to get a. It might be 0, but the point is there's going to be an even number. There's either 0 of them, or 2, or 4, or 6, or 8. And there's always an odd number of 2's in this term. Because there's an even number in b squared, so add one more gives you an odd number.
That's not, is that supposed to be 2 plus b?
No, it's 2 times b
Then it'd be even.
squared. So b,
So it's 2b quantity squared.
b has some number of 2's in it. So b squared has an even number of 2's in it. So 2 times b squared has an odd number of 2's in it. So this term has an odd number of 2's in it. This term has an even number of 2's in it. Not possible because it has the same prime factorization. That's what I'm ultimately saying here. So I'm saying a squared is positive, that's positive, so they both have a unique prime factorization. 2 shows up in a squared even number of times. And I didn't say it very well here, and 2 shows up in 2b squared an odd number of times, which contradicts. Sorry, I didn't spell that out right here. Is there something weird about this?
Yeah.
How does that
How
have an
does
odd
that
number?
prove that it's irrational?
These two numbers have to have the same unique prime factorization, because they're equal. So you can't have an even number of 2's here and an odd number of 2's here, because 2 is a prime number.
Why is there an odd number of 2's there?
So you have 2 times a number squared. Whatever this number is can be expressed as prime numbers. If it has a 2 in here, how many 2's do you want to put in here?
I don't know.
Pick a number.
3.
3. So we have 3 2's in there. When you square it, how many 2's do you have?
6.
6 plus 1 more is
7.
2 times any number you put here plus this 1 is always odd.
Okay.
If this is k, 2k plus 1 is odd.
Okay.
And if you have a k number at a, 2k is even.
That makes
So you always have an even number of 2's in this term and an odd number of 2's in this term. They have to have the same unique prime factorization. You can't have both an even number of 2's and an odd number of 2's. Sorry, I didn't finish writing that this very well.
Okay.
Language isn't good, but the idea there is pretty simple, right? And then the way that we did it before, when we proved that these two things were equal, we got to the same point. We said a squared is equal to 2b squared. Well, first we said, if I can write x is equal to 2 integers m over n, then I can get rid of all the common factors of 2 from it, and rewrite this as a over b, where one of these numbers has to be odd. A has to be odd, or b has to be odd. If they were both even, I could take 2 out of the top and the bottom, and keep doing that until one of them was odd. This is getting to how Euclid's Elements does it. So I can keep doing that until one of these is odd, right? So I have a over b, one of those has to be odd. Well, a squared equals 2b squared, therefore a is even. It's 2 times something. So a squared is even. Oh, missed a step. A has to be odd or b has to be odd, which means a squared has to be odd or b squared has to be odd.
Can they both be odd?
They can both be odd, but at least one of them has to be odd. So a has to be odd or b has to be odd, which means a squared has to be odd or b squared has to be odd. Because the square of an odd is still odd. So either a squared is odd or b squared is odd, right? But a squared is even because it's equal to 2 times something. So, since a squared equals 2b squared, then
And it's even and odd.
a squared is even, which means that there exists k such that a squared is equal to 2k.
Alright.
Because a squared is even.
Yeah.
So if a squared is, well, I shouldn't say it like that, because we need to say a is even. So a squared is even, implies a is even, right?
Not necessarily.
If a was odd,
Oh, then it would be odd.
then it would be odd, so a is even. So a squared is even implies a is even, implies a can be written as 2k, implies a squared can be written as 4k squared, right?
Okay.
You follow the thinking there?
Yeah, what are you doing now?
A squared is equal to 2 times something, therefore a squared is even, therefore a is even, so a can be written as 2k, So a can be written as 4k squared, which gives us that 4k squared is equal to 2b squared, which gives us that 2k squared is equal to b squared. Therefore, b is even. And remember, a or b had to be odd. A or b has to be odd. We just show that this is true. Then they're both even. Which doesn't work. I thought that's, I mean, I didn't write it here very good, but I thought we did that approach earlier in class. Maybe we
It's
didn't.
kind of proving that it's not rational, not necessarily. Right? It's not, right? That's what we're
Right,
saying.
we're saying it's not rational. So it's irrational. Irrational means you can't express it as a quotient of two integers. Whatever that number is, it's not a quotient of two integers. And there's more proofs of this. There's a lot of proofs of this fact, actually. So,
Is this how you prove it? Any number is irrational? Kind of the same.
it's a common way to show that a number is irrational. We often do more generic proofs. So rather than proving that the square root of 2 is irrational, prove that particular types of square roots are always irrational. So we actually have a proof that the square root of any non-perfect square is irrational.
No, what?
If I'm doing the square root of n, if I have the square root of n, where the square root of n is not a positive integer, then the square root of n is not even irrational.
Okay.
That make sense? So in other words, if you're not taking the square root of something like 16, 25, 36, if it's not a perfect square, then it's irrational. It's not even rational. So if your square root of a whole number doesn't come out as a whole number, then it's not even a rational number. It's irrational.
So, does that imply that every decimal square root never comes out to a whole number?
No. Every real number can be expressed as a decimal number. And the square root of 2 is a real number. And when you square it, you get
2.
U2. So, no. Now, every rational number can be expressed as a repeating decimal.
Right.
And every repeating decimal can be expressed as irrational. So, if you make that qualification, if you force it to be a decimal representing a rational number, then you could say that.
Oh, so this is saying that whenever n is a whole number.
Right, so for whole number n's, if the square root doesn't come out as a whole number, then it doesn't even come out as a fraction.
So at the, okay. So it'll never, so the square root of an integer will never be a rational number.
It will either be an integer or irrational.
Okay, great.
Yes. In fact, you can say, well, in this class we include 0 in the natural. So, in this class you could say it will either be natural. The square root of a natural number is always natural or irrational.
Is it more common to say 0 is or isn't a natural number in most courses?
It's hard for me to count in my head. I personally like including it as a natural number. I think it's stupid not to include it as a natural number because, it's the additive identity, and you want to include the additive identity in the natural numbers. So if I want to take the natural numbers and include an operation like addition, I want 0 in there. I want the additive identity. So I think it's dumb not to include it, but a lot of books don't include it.
Why?
Well, for one, you can kind of define things however you want. And then there's the idea of then you have, I mean, then it captures the idea of positive numbers. I mean, to know the author's preference and why they have that preference is a hard thing to know. Typically, they'll just say, this is how they define it in their class. And they'll, in their book, and they'll explicitly say it. I think it, I mean, obviously, I don't know what rationale leads them to not include it, because in my mind, it doesn't make sense not to include it. But it makes defining things like positive real easy. A positive number is a natural number, and now there's a real easy way to define it.
The other way's pretty easy too.
To define a positive number,
Yeah. It's just a natural number that's not zero.
a natural number that's not zero. Yeah, I guess, but that doesn't quite work because, well, of course what I said doesn't really work because that's only the positive
Or
integers.
any number greater than zero, basically.
Well, you use positive to define greater. You don't do it the other way. We say that A is greater than B, provided that A minus B is positive. You need to do it one way or the other. You can either use this to define positive, or you can use positive to define that. It actually doesn't matter which way you go. You just have to go, you have to include something as an axiom and then use it to make a definition. Called them positivity axioms on the real numbers. Anyways, that's not what we're doing today. Well, this is all we were doing. Should have turned off the recording. We're done. So you have the rest of class to prepare